Okay, so in this lesson, we're going to do momentum. What is momentum? How to solve questions. And a very common question regarding relative speed rule, which is point number 4. We will discuss that in detail. How to use that trick to solve questions without even getting into the equation of momentum. So the first point is the principle of conservation of momentum. It totally suggests that the momentum of the system after the collision will be equal to the momentum before collision. So momentum before collision of all the involved bodies will be equal to the momentum after the collision of all the involved bodies, while there is no external force acting, right? So the main idea would be that if, for example, there is an object A and there is an object B, they are colliding or they are going to collide, and let's say that they either separate or they continue to move in the same direction, their masses will be given, right? So if this is m1 and this is m2, this will suggest that if this is UA, this is UB, and this is VA, and this is VB, suggesting initial and final, the equation will become something like this, that before collision, the whole system actually looks like this. And we know that velocity will be following the vector convention in terms of its signs. So before it will be m1, since VA is moving towards the right side, it will be a positive velocity, plus m2, but U will be put as a negative sign because it's moving towards the left side, is equal to that in the after condition. That will be placed like this, that if VA is moving towards the left side, it will be negative, and VB will be positive. So this will become M1 with the negative VA plus M2 with the positive VB. So that is how the first law or the first point is being applied. The second idea is about conservation of momentum, and it only means that in terms of elastic and inelastic, that kinetic energy will be conserved or not. We're familiar with this idea from O levels and IGCSE that in an elastic collision and in an inelastic collision, the only difference is the conservation of energy. So in the first elastic collision, we have the momentum is conserved. And even in inelastic, the momentum will be conserved, which means that we can use the principle of conservation of momentum to solve those questions, either for elastic or either for inelastic. The only difference between them is for kinetic energy. In this case, the kinetic energy is conserved, but over here, the kinetic energy is not conserved, right? And we will solve a few questions to apply this rule in detail, how we can simplify or how we can see that whether this collision is elastic or inelastic. And when this is inelastic, what generally means that the kinetic energy possessed by the objects before they were incoming or as they're moving away has been lost to the surrounding as either thermal energy due to a change of shape because the bodies are elastic, or they can compress under each other's force during the collision, or it is sometimes you lost as sound energy, right? Okay, so we have also looked at point number 2. Point number 3 is relative speed of approach. We'll get to that later. And the fourth point is about the change in kinetic energy. So let's look at point number 3. Point number 3 requires, okay, so there is one more thing about the dimensions being involved. So we also have to look at the momentum in terms of, or momentum collision in terms of 2 dimensions. We'll do that question that is at the end of this lesson, which involves the collision of objects in 2 dimensions. And most definitely we'll be involving vectors and vector components to solve the system, right? So I'll discuss the 2-dimensional vectors at the end. Okay, so the relative speed rule, this is the most common misconception in terms of momentum questions. This is generally skipped in classes, but we'll get to see that without this rule, you will be unable to solve many questions. So the first point that you're supposed to remember for this rule is that it is only applicable for elastic collisions, right? And point number 2 is that since it is elastic, the mass will be irrelevant for the question. This rule, or you can say this trick, the best thing about this is that mass is not required to be involved in the question to solve the question. If the mass is given, that is also okay. If the mass is not given, that is also fine. We'll also look at an example in which this is the case. Masses will not be given to you. So students generally get confused at how are we supposed to solve this question. The main simple idea is that for an elastic collision, the relative speed rule will be applied and the masses will be relevant. Now, a simple trick to identify whether a collision is elastic or inelastic is that in many cases, in approximately 99% of the times, inelastic collision will cause or will require, or you can say that the after the collision, the objects will stick together or they will be embedded in one another. For example, if a bullet is being fired into a wooden block, that bullet will be embedded into the wooden block after the collision, right? For example, if two vehicles are incoming towards each other, they collide, they have an accident, and they stay fixated amongst each other. They stay fixed in one another and are unable to separate because the accident is so violent. Even in those cases, though, they will be considered as inelastic collision. So this is a simple trick in which you can very well see whether you can or cannot use the rule of relative speed, right? Okay. So what are the equations and how we will see them? Now, in generally in questions of momentum, we know that the right and upwards direction of velocities are considered to be positive and downwards and left are considered to be negative. Over here, the rule will be slightly different. We don't involve the signs for the direction, but we only involve them to understand which direction they are moving, but we will not involve them in the calculations. Let's see an example how to observe this. Now, for example, it could be a before system, it could be an after system, it does not matter. The rule will still be applied. So one of the cases is that, for example, if an object A and object B, they are moving in the same direction, that is towards the right side. And in another case, let's say there is an object A and object B that are moving towards the left side, but it will be spoken as same direction. So in this case, their velocities will be subtracted. Now, in both of these cases are basically of subtraction because in terms of relative speed compared to the other object, since they're moving in the same direction, their speeds will be subtracted. Now, let's call the speed as VA and let's call this as VB. Similarly, this will be VA and this will be VB. We'll get to the later how to make that equation. Now, the third case will be, let's say that both of the objects, object A and object B, are moving towards each other. And in this situation, we'll call them VA and VB. In fourth scenario, they are moving, let's say, apart from each other. Even in this case, it will be called VA and VB. Now notice that for this relative speed rule, you don't have to involve the negative direction. We know that in second case, they are both moving to left side. So I should add a negative sign. We don't have to do that in this case. Yes, negative sign will help you understand where this object is moving, for example, but it will not be involved in the equation, right? Okay, even in this case, let's say this is towards the right side, this is positive, and this is left side, this will be considered as negative. But over here, we will see that these signs will not be involved in the calculation. In this case, the speeds will be added together. Now, simply, subtraction will occur if the objects are moving in same direction. If the objects are moving in opposite direction, now opposite would mean one is left, one is right, as explained in this case, you will simply add the velocities. Velocities will be added irrespective what is left, what is right. We will not involve the sign. I repeat, we will not involve the sign in the calculation. We will only involve the sign to visualize the direction. That is it. So let's do the addition case first because subtraction requires a bit of understanding. So in addition, we know that since they are moving in the opposite direction, I can simply add their values. So this one, the first case will become VA plus VB. Now notice that VB is moving towards the left side, but I have not involved it in the calculations. Be advised, this negative VB will not be involved here. So let's say if this is moving at a speed of 6 meters per second, this is moving at 3 meters per second, this will not be 6 minus 3. This will be taken as 6 plus 3 according to the relative speed rule. Similarly, in this case, let's say this is moving left towards with 5 meter per second and rightwards 7 meter per second. Even in this case, if they are moving in the opposite direction, they will be added together. Now notice I will not be adding a negative sign, but yes, negative sign does give me the information that it is moving towards the left side. So, and this positive tells me this is moving towards the right side. This helps me understand that this will be an opposite direction case, right? So I will simply add their velocities as 5 plus 3, 5 plus 7. This will become 12 meters per second, right? Okay, now for subtraction in same direction, there is a condition that we need to understand, which I just explained in this case, that the objects, if they are sticking together, they will be inelastic. Inelastic, they are supposed to be separated even before and after collision. It is impossible for both objects to collide again or to be uh, embedded as one. So in case number one, if we see this VB is in front of VA, right? This is in front of VA. Now, if the collision has already taken place or the collision is about to take place, before the collision, we can say that VA may be greater than VB, right? So that it can eventually catch up to VB. But after the collision, that is where it gets interesting. VB has to be greater than VA because they cannot embed together, they cannot stick together, they cannot join together even after the collision, or a second collision cannot take place. So this will be a relative speed idea or an elastic collision idea. So based on this idea that after collision, VB has to lead, it has to be faster than VA. So the equation will become, VB minus VA. Although a student could have written down VA minus VB, it should have been right, it would have been right because we're taking subtraction, right? So there's no compulsion which should be subtracted from which factor. But in this case, it is a compulsion that the leading object has to be faster, and that will be subtracted from the object that is trying to catch up to that object, right? So this equation will be incorrect. Similarly, in the second case, we must understand that VA should be greater than VB to avoid sticking together or a second collision after a collision, right? So this will simply become VA minus VB. So what students generally memorize this as that the object that is leading upon separation or upon same direction minus the object that is lagging behind, right? And we will use this idea, we will use this rule to solve many questions, and you will see that mass is irrelevant in this situation. Even if this was 3m and this was, let's say, only m, the answers will still be the same and answers will come out as the correct answers because the underlying assumption is that the collision is elastic, right? So let's move towards solving questions. Okay, so one proof that is generally a part of your course. It is understood that you already know this from O-levels or IGCSE, but I'm going to go through that again. So the formula is F is equal to MA, and from kinematics, very basic kinematics, we know that the formula is V minus U divided by T. If you replace this formula into this equation, that becomes F equals to M into V minus U divided by T. If you perform algebra onto this and multiply M on both sides, this becomes MV minus MU divided by T, and this F as it is. So we know that V is final velocity and U is initial velocity. By that idea, I can simplify because I know that momentum is equal to mass into velocity. So I'm going to combine this as final momentum minus initial momentum divided by T. Now, to simplify this further, since this looks like a change in momentum, I will simply write down delta P divided by delta T. And from this point onwards, if this T is taken to the other side, it becomes F multiplied by delta T equals to delta P. Now, one of the sides is referred as impulse. This is referred as impulse, and this is referred as simply change in momentum, right? So sometimes, but most of the times, the equation or the question will refer to as an exertion of force, or a force is exerted or applied with respect to a change in momentum, or a ball, let's say, colliding with a wall and bouncing back. So how much force has it exerted on the wall? So in those cases, we know the mass of the ball, we know the incoming velocity, we know the outgoing velocity, we know for how long the ball has stayed in contact with the wall. Let's say it's 50 milliseconds or 30 milliseconds, and then it started to go back. we can put these values into this equation or into this equation and find out the average force exerted by the ball on the wall. And of course, due to Newton's third law, the wall will also be exerting a force on the ball. We'll also look at such a question in the MCQs as well. Now, let's move towards a simple question that involves conservation of momentum. So it says that these two objects are moving towards each other. One thing that students generally ignore in such questions is when he says that they are equal masses. Another word he will use for this situation is identical masses. And one more thing, it says that it sticks together on impact. This gives me a 100% hint that this is going to be an inelastic collision, right? So let's solve that system. We have a before collision system, and he says that they stick together and then start moving towards this random direction. I don't know what that direction may be, but we will be able to predict what that direction may be if he asks us. Now let's make the equation that is momentum before collision should be equal to momentum that is after collision. So before collision says the speeds are in 6 centimeters per second. The final answers are also in centimeter per second. I don't need to convert this into meter per second. It will not serve me any benefit. So mass into velocity plus mass into velocity is equal to mass into velocity plus mass into velocity. This is what the equation would generally look like, but let's put in the values. So before impact, we have, since they're identical masses, I'm going to assume a variable m for both of them. It doesn't matter. So this will be m into 60 plus m into, now notice that for 30, I should put in a negative sign because it's moving toward the left side. So this is 30 equals to, now since they are sticking together, it means that their masses should be added together. So this will be 2m into v. This is the v that I don't know. How would this become 2m? Because we are adding both masses, so m plus m should become 2m. Now on this side, I get, on the left hand side, I'm only left with 30m equals to, on this side, I'm left with 2mv. Now simply performing the algebra, we can see that m gets cancelled out, right? So we are left with 30 is equal to 2v, which means that v is equal to 15 centimeters per second. So the answer of this question will be option A. A very simple, very easy question to understand, to first just understand how we are going to use the law of conservation of momentum, right? Okay. So moving on to the next question, it is somewhat similar, but okay. So one thing over here, since we have involved the left direction to be negative, if this velocity is positive automatically, right? That means that after sticking together, both objects are moving towards the right side with 15 centimeters per second. Although it's not asked in the question, but we can predict that direction. Similarly, in this question, it has no clue about the direction, but it only says that it is moving in the opposite direction. So it says that a mass of 20 is moving at 6 and a mass of 12 is moving at 15 in the opposite direction. So we can assume this question in any way possible. It's possible that you assume the 20 kg object to be moving towards the right side with 6 meters per second, and this 12 kg mass moving at 15 meter per second in the opposite direction in this way. Or you could have visualized this 20 kg to be moving towards this side with 6 meter per second, and this moving towards this side, the 12 kg with 15 meter per second. It will not change the outcome of the answer because the direction is not asked. So I'm going to go with this simple understanding, right? This one, and it says that they are going to stick together, again, an inelastic case. So why am I referring to this again and again? Because this will help us in the relative speed rule to figure out whether the relative speed rule should be applied or should be checked or not. Is it worth wasting the time on that or not? So in this case, this becomes 20 multiplied by 6, positive 6, because it's towards the right side, plus 12 mass into minus 15, because this is moving towards the left side. Then this should be equal to, since both masses are going to stick together, they will be added together. So this will become 12 plus 20 into simply v, the velocity where they're going to go. Okay. So simply after performing algebra, you should land on this answer, which is going to be 1 point, which will be 1.875 meters per second. But since the answers in A levels are going to be up to two significant figures, this will be 1.9. So option A will be your answer. Moving ahead with this question, this is a common question and a conceptual one. It says that two identical spheres, that means that the masses are equal. The masses are equal. It says that y was stationary with 0 meter per second and it's coming at v. Sphere collides elastically, what happens? Now, according to the relative speed of approach or relative speed rule, we understand that before collision, the system will become v plus 0, right? Simply the speeds are going to be added together. Now, after this, what happens or what should happen is that this one will stop and this will start moving. And interestingly, if the masses are equal, this is also one of the trick points of momentum. If the masses are equal and they collide elastically, the velocities exchange. The velocities get exchanged. So this one will now have a velocity v towards the right side, and this one will have a velocity of 0 meter per second, will stop moving. This is what happens in the snooker table situations, and when momentum is being discussed, that example is generally discussed. This is exactly what happens over there as well, that one ball collides with another, the second ball starts moving and the first one becomes stationary, generally if the angles are not involved. So the speed of x will be stopped and it starts moving towards the right side with speed v. A very common question that involves 2 to 3 pointers that should be memorized, that if the masses are equal and the collision are inelastic, the velocities will be exchanged among the objects. And it's applicable for all the cases. For example, if the objects are moving towards each other and then they get separated, most definitely this will have a velocity of this one and this will start moving with the velocity of the second object, right? So second question, this is actually a question coming from pressure of gas. It's actually a question for cricket. It's a question for tennis. It's a question for badminton, that a shuttle or a ball is moving towards the racket and the racket is also moving. So what will happen, right? So in this case, this is the right direction, so this will be positive. And after the collision, it says that it still is moving with the speed of v, right? So the mass is m, but the speed will have a negative sign. Now this is my final momentum and this is my initial momentum. So since he's asking me about the change in momentum, I should simply write down delta p is equal to final momentum minus initial momentum. Now notice that my final momentum is after the collision, so this is m and minus v, so this will become m multiplied by negative v. Now this minus is because of the formula, and then we have m into positive v. Why positive v? Because it was initially moving towards the right side, so this will be positive v. This equation comes out as negative mv minus negative mv, and it simplifies to negative 2mv. Now notice that amongst these two equations, we have, in two options, we have 2mv. This is a and b. C and d will be cancelled because the change in momentum is not mv, it's 2mv, right? Now, since this is a negative sign, this tells me that the change has happened towards the left side, right? So the correct answer for this question will be option B, right? Okay. So moving towards the next question we have, now this is the question that is one of the most common question that creates problem, that creates a bit of an issue in terms of visualizing directions and how this will be solved. And this is a relative speed question. The masses are not given to you. Even if he said that the spheres are identical, masses were given, it does not matter. He says that the collision has to be elastic, which means that the relative speed before approach should be equal to relative speed after the collision or after the approach, right? Now, since initially the objects are moving towards each other, we know from the relative speed rule that if the objects are moving towards each other, I simply have to add them. This is case number 3. I simply have to add their velocities together. So in this case, before the collision, it should be UA plus UB. Again, I remind you that this is moving towards the left side, the negative sign. It will not be involved in the calculations. It only helps us visualize where this is going so that we can figure out whether they're moving in the same direction or opposite direction. And after the collision, now they're moving in the same direction. So I should be using subtraction. So it could be VB minus VA, or it could be VA minus VB. I could have done that, but I will choose VB minus VA. Why? Because I cannot let them collide again. I cannot let them stick together. So my VB should be greater than VA. This should be in leading position. This should be faster. And this one should be slower so that it does not catch up to VB again, right? So the equation becomes, this will not be considered. The equation becomes UA plus UB equals to VB minus VA. And we can very well clearly see that this is the option A. This question is from 2002. but it is repeated many times in the recent years as well. And students generally don't understand this, so they memorize the answer that it's going to be A. So what the examiner started to do was he started to shuffle the options and shuffle the question a bit, right? So please be advised that there is a reason, there is a logic behind this, and this is how you solve it. Okay. This is again a relative speed question. So it tells me that both objects are moving towards each other. So since I know they're moving towards each other, I'm going to simply add their speeds. So this will be 5 plus 15 before collision. The relative speed is 20 meters per second. Now the after collision, it tells me that y moves towards the right side with the speed of 7. So y is moving towards the right with 7 meters per second. So I do have the velocity of y. So after collision, it will become 7 plus something, which will be the speed of object x. That should be equal to 20 meters per second because the relative speed before was 20. So now I'm supposed to figure out what that speed should be. Now notice that I have an option of 3 and 3. 3 and 3 will not be possible because no matter if I add 3 in this equation or I subtract 3 from this equation, irrespective of the direction, I'm not going to get 20 in any way possible. So 3 is not the possible answer. Now I'm left with option B and D. I know that 13 has to be added over here in the after case, so that this eventually becomes 20 meters per second. Now, in order for me to add this, or in order for me to be able to add this, it means that both objects should be moving in the opposite direction. They should be separating from each other, or they could have been moving towards each other for me to be able to add them, right? So in this case, it should be moving 13 meters per second to the left. Only then I can add it and make it 20. If it had been moving 13 meters to the right, that would null the equation and that would give me a false answer because 7 meters per second to the right and then 13 meters per second to the right. Since they are both moving in the same direction, I should have subtracted them, which will give me an answer of 13 minus 7. And another problem over here is that actually goes against the principle of elastic collision, and that the leading object, the y, should have a higher speed than the object that is coming after. So that could not have been an elastic collision. It would not be an elastic collision if that was the case. So option D gets cancelled out because of two reasons, right? First, mathematically it's impossible. Second, for it to be elastic, it should be moving slower than the object that is leading it, right? Okay. Now this is a question that I was referring to again and again. The negative sign does add into the system or is a part of the question, but it only helps you visualize where the objects are going, where the objects are moving, so that you can calculate the relative speed. Now in option A, we can see that u1 is 2 and u2 is 5. It's minus 5. So what option A means is that before collision, the first object is moving towards the right side and the second is moving towards the left side. Similarly, on the other hand, after the collision, which is the after case, we have minus 5 and minus 2, which means that the first one is moving towards the left and the second one is also moving towards the left. So this is 2 meters per second. This is 5 meters per second. Notice I have not added the negative sign because it's not required in such questions. And in the second case, we see that at both negative speeds, so I will put minus 5 and 2, but towards the left side. Now I know from relative speed rule that if they're moving in the same direction, the speeds are supposed to be added together. So this becomes 7 meters per second. And if they're moving in the same direction, which is right now towards the left for both of them, I should subtract them. So this will be 3 meters per second. He says specifically which one is not elastic. We know that in which relative speed rule fails, that will be a non-elastic case. So the answer is option A, but for the sake of practice, we will apply this rule for the other options as well. The answer is A. But let's apply this for option B as well to fully understand the concept. Now 3 and minus 3, that would mean that one object is moving towards this side and the other is moving towards this side. Again, 3 and 3. And after collision, one of them is not moving and one of them is moving towards the right side with 6 meters per second. So if relative speed is applied, opposite directions, they should be added together. So 3 plus 3 gives me 6 meters per second. And over here, 0 plus 6 gives me 6 meters per second. So this is an elastic case. Because only in elastic cases, these options are going to be applied or give you the correct answer in terms of relative speed. So option C, we have 3 and minus 2, which means that an object is moving towards the right side with 3 and towards the left side with 2. And after collision, one of them is moving towards the right side with 1 meter per second and the second object is moving with 6 meters per second towards the right side. Notice one other thing, that the leading object has a higher speed and the lagging object has a lower speed. So it looks like an elastic case, but let's, for the sake of example, solve this. So this is opposite direction, so this will be 3 plus 2 as 5 meter per second. This is same direction, so it will be subtraction, so 6 minus 1 leads to 5 meter per second. Again, before and after, exactly the same speeds in terms of relative speed. In option D, we have 5 and 2. Since they are both positive signs, 5 and 2, it means that both are moving in the same direction. This is 5 and this is 2. So before collision, we understand that the lagging object, the object that is behind, has to have a higher speed so that collision can take place. It will eventually come up to this collide and then start slowing down than the first object, right? Okay, the second idea, 3 and 6, that means that this one is moving at 3 and the first object is moving at 6. So relative speed suggests that same direction should be subtracted. So this will be 5 minus 2, giving us 3 meters per second. And this will be 3 minus or 6 minus 3 because they are same direction. So this will be 3 meters per second. Again, before and after, the speeds are similar. The relative speeds, sorry, are exactly the same. Hence, this will also be an elastic case along the rest of them. So the only inelastic case we have in this case is option A, right? Okay. Now, moving towards this question, this is from October, November 2020, one of the latest questions. Notice in this question that the velocities are given and the masses are also given. And in this question, we will apply the kinetic energy principle to verify whether the relative speed rule gives us the correct answer or not. But first, we will solve the question using the relative speed rule. Irrespective, now since he says that it is not elastic, that means that the relative speed rule will fail in one of the options. And what is that option? Let's try to visualize that. So I'm not drawing the directions again because they're already given in the question. So since they're moving in the same direction in option A, the answer in this case will be 3 meters per second for relative speed. In this case, after the collision, they're still moving in the same direction. 5 minus 2 gives me 3 meters per second. So this is not the answer because the relative speed before and after is equal, which means that this is an elastic collision. For option B, again moving in the same direction, this will be 3 meters per second. And 7 minus 4, again same direction, this will again be 3 meters per second. So a relative speed of approach is equal to relative speed of separation. This is an elastic case. In option C, we see 8 and 2 moving in the same direction. So this should be 8 minus 2. This will be 6 meters per second. But after the collision, we see this is 8 and 5. Same direction, we should subtract them. So 8 minus 5 will give me an answer of 3 meters per second. Although this is my answer, but in the interest of practice, we're going to do that again. So 10 and 4, same direction, so they should be subtracted. So this will be 6 meters per second. 6 and 12, same direction, should be subtracted. So 12 minus 6 will give me 6 meters per second. So this is also elastic. The only inelastic system that we have is option C, which actually failed the relative speed test. Now, for the interest of science, let's apply the kinetic energy principle for both options. Although you can do this for option A and B as well, but I'm going to only do this for C and I will do this for D, so that we can understand that relative speed rule does give you the correct answer irrespective of the mass. You see, we did not even think about the masses for this question, right? We are now going to involve the masses to find out the kinetic energy and then see whether this relative speed rule gives us the correct answer or not, right? Okay, so moving towards, so for option C, we are going to apply the kinetic energy before and after the system. So simply put, the equation will look something like this. This will be 1 over 2, right, into mass of the first object, which is 2m, as given over here, and the second is m. The velocity is 8 square plus 1 over 2 into mass of the second object, which is m into 2 square, right? And this should be, is this equal to or should be equal to the system that is after the collision? So let's equate both of them. So 1 over 2 into 2m into 5 square plus 1 over 2 into m into 8 square, right? So in this case, you will find the answer of the left hand side to be 66m and the right hand side to be 57m. So since kinetic energies are not equal, this is an inelastic collision, right? Now let's apply this same idea for the option D. So 1 over 2 into 2m into 6 square plus 1 over 2 into m into 4 square equals to 1 over 2 into 2m and 6 square, because we're kinetic energy, so half mv square is the formula. So this will be 6 square plus 1 over 2 into m into the after speed is 12 square. So 12 square. So in this case, you will get the left-hand side to be 108 m and the right-hand side to be 108 m. So since the kinetic energies are equal, option D was elastic. You can do the same thing for option A and B and get the same answer for before and after. But for option C, you will not get the same answer. And the problem is that if you get involved in this kinetic energy calculation, it will take you a lot of time to actually figure it out. So this is the hint for you to actually involve the relative speed rule to figure out whether this is elastic and inelastic. And for the sake of intellectual curiosity, you can solve the question using a kinetic energy principle to eventually get the same answer. So we will save our time by using relative speed rule, and we will not indulge in kinetic energy principle unless it is absolutely necessary. This is another question. Again, in this case, the directions are given, and let's say that we have to apply for perfectly elastic. The relative speed rule should hold, and in this case, very easily I can figure out that option A and B are incorrect. Why? Because they are the example of sticking together. So I will not even check option A and B, and I will only look at option C and D. You can, however, verify through kinetic energy principle, like we have done in this question, to see that A and B will come out as inelastic, right? Because the kinetic energy is not conserved in both of them. So option C, since they are moving towards each other, the relative speed will be 3 meters per second. They will be added. In after collision, they are moving away from each other, so they should be subtracted. So 3 minus 2 gives me 1 meter per second. The inelastic collision answer most likely is option C, right? So uh, let's move towards option D. Sorry, this is inelastic. So since he's asking me about elastic, option C is inelastic because the relative speeds are not equal. But for the sake of understanding, we are going to solve the third part as well. So 4 and 1, same direction, they should be subtracted. So 3 meters per second, and 1 and 4, they should be subtracted. So this will be 3 meters per second. And notice one thing over here. Just as I mentioned that if the masses are same in one of the questions, let me show you that question again. In this question, I discussed that if the masses are equal, the velocities will interchange if thus it is an elastic collision. You can see this in this example as well, that the masses were same, the masses are same, and you can see that the velocities are exchanged. The next object, the first object is moving at 1 meter per second, and the second one is moving at 4, whereas before collision, the cases were reversed, right? So even this hint was good enough for you to figure out that it is D. But for the sake of solving, or to be able to solve, you can employ any technique that you want, right? The next question is about, this question is taken from May, June 2016, and the variant is 23. I'm skipping the definition because you can see that from the marking scheme. Although I'm going to speak it out. Law of conservation of momentum would mean total momentum before and after collision is same when an external force is not applied, right? Now, this is a two-dimensional momentum question. Be advised that you cannot solve this question just involving velocity or just involving mass. Since this is a momentum question, both quantities should go hand in hand, even for vector components, even for solving the question. So it does tell me that VA is moving at 500 meters per second, B is at rest, and the masses of each particles M is already given to you, which is 1.67 power minus 27. Now, this number actually tells me that this is from atomic physics, and these might be protons or neutrons present outside the nucleus, right? So it tells me what is meant by elastic collision, right? So total kinetic energy before and after collision remains same. Now he calls me to calculate the total momentum before the collision, which is A and B. So I can simply apply mv plus mv. Now, since particle B is at rest, I don't need to involve this in the calculation because its v will become 0 and the whole factor becomes 0. So this is 500 meters per second multiplied by the mass of the single particle, which is 1.67 into 10 raised to the power minus 27 kgs. So the momentum's answer comes out as 8.35 into 10 raised to the power minus 25. But since it's two significant figures, we're going to round it off to 8.4. Now notice the unit of momentum, that is Newton seconds. Don't need to worry about that because if we go back to the proof that we just did over here, we notice that on left hand side, this is Newton multiplied by seconds equals to change of momentum, which unit is kg meter per second. So both units are interchangeable. It does not matter. Okay, so the next question, he says that find out in terms of MA, VA, and VB the total momentum in the x-axis direction and y-axis direction. So it's generally going to talk to you about the momentum in terms of vector components. So along the x-axis, we can see that, let me erase this and make some space for this, right? So for VA direction, we have this one, right? So this will be MA VA cos of 60. And this direction of momentum will be VAM sine of 60, right? Similarly, on the other hand, if we look for the component of particle B, that will still be in this direction with the MBVB cos of 30. And this component will be MBVB sine of 30, right? Okay, so we can see that we are involving mass and velocity both as a part of the equation. Okay, so along the x-axis, I can see that there are two components that both are in the same direction. So I will have to write them both. So this will become M. Now, since we don't, we know that masses are exactly the same, we don't have to write down MA and MB because we know that both particles are exactly the same mass. This is what he says. The mass of each particle is this. So I just wrote this down for an individual idea, but we are going to keep M same in this equation. So this will be MVA cos of 60 plus MVB cos of 30. We can see that these are the two components along the x-axis. These are the two components along the x-axis. And along the y-axis, we have MVA sine of 60 plus MVB sine of 30. Now notice one thing before we start the question. This is the main idea of the two-dimensional momentum question. We know that before the collision, there is only momentum involved or available along the x-axis direction. The particle is not moving up, it's not moving down. There is no y-axis momentum present in the question. So the y-axis factors that are introduced in the question means that they should be either exactly equal or adding them together should give me a zero answer. Because momentum along the y-axis should not exist because it was not brought into the system. It was not part of the system. It was not introduced in the system. The only introduction of momentum was along the x-axis. So only x-axis should be solved. Y-axis should either cancel out or they should be equal. So one way to look at this would be that either VAM sine 60 is equal to MVB sine of 30. They're exactly equal. So they cancel each other out and the resultant answer should be 0 along the y-axis. Or they should be written down like this: VAM sine 60 minus MVB sine 30 equals to 0. Although this will actually be an addition but with a negative sign of this factor because they're opposite to each other. So their addition should be 0. Okay. So over here, this is simply written down as simple algebra because we know that one of them will be actually as negative. And when the one of them is negative, if it is equal to 0 taken to the other side, this will become positive, right? Which gives us back to this equation that both of them should have been equal. Okay, now he tells us to solve this question by using the algebra. Now we notice that to simplify the equation, we can simply remove m from the whole equation because it's exactly the same for all particles. We don't need to involve it to further complicate the situation. It's not needed. So let's rewrite the equation along the x-axis or the x-axis components. The true equation will be mVA cos of 60 plus mVB cos of 30. Now we know that the x-axis momentum that was brought into the situation was mv because of this moving particle, right? So since this momentum was already calculated as 500 multiplied by mass, let's keep mass out of the equation and write this down as 500 m. Be advised, notice that if I do involve mass into the equation, then the mass would have to be written down here, here, and here as well. So since it's exactly the same across the board, I'm going to simply cancel it out. like this. Okay, so this equation generally becomes, or eventually becomes, VA cos of 60 plus VB cos of 30 equals to 500, with mass actually settled on both sides. Similarly, on the y-axis, we have this equation now eventually, that both of them or their addition should be equal to 0, because y-axis momentum was not introduced in the system. It never came from anyone. So we have VA sine of 60 plus VB sine of 30 equal to 0. Now, they should be put something like this: VA sine 60 minus VB sine 30 equal to 0. Now, notice that he asks you about VA and VB, and they will be solved simultaneously. The problem is that the examiner does not care about the algebra that you're going to perform over here. This will be the final equation for y-axis, and this will be the final equation for x-axis. We need to solve them simultaneously. Now, you're going to employ the techniques of mathematics that you've already done, using quadratic equations, using the formulas, using substitution method, using elimination method. The problem is that it's going to take a lot of time. So what we're going to do, we're going to use the calculator to solve this question and see what it does for us, right? So we simply go to the menu, we go down to the option of equation and function, right? And then press equals to. It asks me, what do you want to do? We want to solve a polynomial, or what do you want to solve a simultaneous equation? So we're going to choose one. It's asking me how many number of unknowns. So we are dealing with two unknowns, VA and VB, x plus y, right? So I'm going to choose 2. It gives me an equation that looks like this. I'm going to straight away put in the values as it is that they're represented on this screen. So VA will be my x and VB will be my y. So cos 60, so I'm going to write down cos of 60, bracket close, press equals to. It will calculate this cos 60 for you and put in the value. Then we have cos 30. So this would be cos of 30, bracket close, press equals to. And on the other hand side, we know that it is equals to 500. So press equals to. Notice that the calculator should be in degree mode, not in radians, because you're dealing with components, right? Components and angles. So it should be in degrees. Then we simply replace 60. Sine 60 is equal to this. But now be careful. Here we should write down minus sine of 30 degrees, bracket close, press equals to. And we know that the other hand side, we have a 0 sign. Press equals to, and it tells you the calculated answer. One of them is 250 and the other one is 433. Now be advised that the variable that you put as first was VA, right? And the second one was VB. So this is basically the calculated x and this is basically the calculated y. So it tells you that the variable x was 250 meters per second and variable y was 433 meters per second, which means that this was actually in place of VA and this was in place of VB. So your answer will be 250, and for this one, this will be 430 because it's supposed to be taken as two significant number. Be advised, you are allowed to use this technique. You are allowed to use this method in your examination. Please don't shy away from using the calculator up to its full potential. You don't have to waste your time solving this simultaneously. I hope that we have learned how to use that simultaneous function and how to save time in this situation, right? Okay, that is all for today.